What do we mean by the term allotrope? Allotropes are different forms of an element which have different physical properties but identical chemical properties. Different allotropes of the same elements have different arrangement of the atoms. Carbon exists in both crystalline as well as the amorphous forms. There are three important crystalline allotropic forms of carbon: diamond, graphite, and fullerenes. Diamond, the first allotrope of carbon, is the hardest substance on Earth. Diamond has a crystalline lattice in which the carbon atoms are arranged in a rigid three-dimensional network. In diamond, all carbon atoms exhibit sp3 hybridization. Each carbon is bonded to four other carbon atoms situated tetrahedrally around it. The CC bond length is 154 picometers. This directional network extends in space and produces a three-dimensional network of carbon atoms as shown in the illustration. Try to answer this question yourself before proceeding. The carbon atoms in diamond are covalently bonded. Why is the melting point of diamond very high? Recall that each carbon in diamond is attached to four other carbon atoms surrounding it. It is very difficult to break up this covalent network as it is very rigid, and hence diamond melts at an extremely high temperature. Since there are no free electrons in a diamond crystal, it is a bad conductor of electricity. Another important allotrope of carbon is graphite. You are probably the most familiar with this form of carbon for its use in pencils. Despite the name, pencil leads are actually made of graphite. Graphite has a layered structure. These layers are held together by the weak van der Waals forces of attraction. The distance between any two successive layers is 340 picometers. Each layer of graphite is made from planar, hexagonal rings of carbon atoms as shown in the diagram. All the carbon-carbon bonds are 141.5 picometers in length. Each carbon in graphite is sp2 hybridized. Each atom forms 3 sigma bonds with its 3 neighboring carbon atoms. The fourth electron of each carbon is involved in pi bonding, using the unhybridized p orbital on each carbon atom as shown in the illustration. The electrons involved in the pi bonding are delocalized. This means that they are free to move, and thus graphite is a good conductor of electricity. Try to answer this question on your own before proceeding. Why is graphite soft and slippery? The layers in graphite are held together by the weak van der Waals forces of attraction. Thus, the layers slide past over each other and break off easily. When you take notes with your pencil, you leave layers of graphite behind on the paper. The third important allotrope of carbon, the fullerenes, are the most recently discovered. They were identified by Robert Kerr, Harold Kroto, and Richard Smalley in 1985, for which they were awarded the 1996 Nobel Prize in Chemistry. Fullerenes can be prepared by heating graphite in an electric arc in the presence of inert gases. This work led to the discovery of the two most important fullerenes: molecules containing 60 and 70 carbon atoms, respectively, plus traces of other fullerenes. Fullerenes are cage-like molecules. C60 or Buckminster fullerene, named after the American architect famous for his geodesic dome structures, looks like a soccer ball. It is sometimes referred to as a buckyball. Buckminster fullerene contains 60 carbon atoms arranged as a hollow sphere. This ball-shaped molecule has 60 vertices, each occupied by a carbon. It contains 20 6-membered rings and 12 5-membered rings. A 5-membered ring is fused with only 6-membered rings, while a 6-membered ring is fused with 6 or 5-membered rings. All the carbons in the Buckminster fullerene molecule are sp2 hybridized. Each carbon atom forms 3 sigma bonds with its 3 neighboring atoms. The remaining electron in each unhybridized p orbital of carbon is delocalized in molecular orbitals, giving the aromatic character to the molecule. 2 different bond lengths are observed in Buckminster fullerene. The carbon-carbon single and double bond lengths, as observed in C60, are 145.3 and 138.3 picometers, respectively. Each carbon atom forms formally 2 carbon-carbon single bonds and 1 carbon-carbon double bond. Under standard conditions, graphite is the thermodynamically most stable allotrope of carbon. Since it is considered as the standard state of carbon, its heat of formation is set at 0. Both diamond and fullerenes have higher heats of formation, reflecting their lower stability. The heat of formation of diamond is 1.90 kJ per mole, and the heat of formation for fullerene is 38.1 kJ per mole. The amorphous forms of carbon include carbon black, coke, and charcoal. Carbon black is formed by burning hydrocarbons in a limited supply of air, or by incomplete combustion. It is an almost pure form of amorphous carbon containing 98 to 99% carbon. Coke is formed when wood is heated at high temperatures in the absence of air, which is called the destructive distillation of wood. To form charcoal, coal is heated at high temperatures in the absence of air. Carbon has a wide variety of uses in its elemental forms. Diamond is widely valued in jewelry. They are measured in carats. 1 carat is equal to 200 milligrams. Diamond, both natural and synthetic, is used as an abrasive in sharpening tools, die making, and in the manufacture of tungsten filaments for light bulbs. Graphite is used as a dry lubricant in machines running at high temperature where oil cannot be used. Graphite is also used to make strong and lightweight composite material for tennis rackets, fishing rods, aircraft, and canoes. Being a good conductor, graphite is used to construct electrodes for use in batteries and in industrial electrolysis. Crucibles made of graphite are inert to dilute acids and alkalis. Activated charcoal is very porous and can absorb many times of its own volume of gases. It is used for adsorption of poisonous gases, removal of organic contaminants from water, and for odor control in air conditioners. Carbon black is used as a black pigment in black ink and as a filler in automobile tires. Coke is used as a fuel and as a reducing agent in metallurgy. We'll start with the oxides of carbon. Carbon monoxide with the chemical formula CO, and carbon dioxide Carbon monoxide is a colorless, odorless gas that is nearly insoluble in water. The carbon monoxide molecule contains one sigma bond and two pi bonds, as shown in the illustration. There are several ways to prepare carbon monoxide. The first way is the direct oxidation of carbon in a limited supply of oxygen or air. The reaction shown here is an example of incomplete combustion. Another way to prepare carbon monoxide is the dehydration of formic acid, also known as methanoic acid, with concentrated sulfuric acid at 373 Kelvin. On a commercial scale, carbon monoxide is prepared by passing steam This reaction produces carbon monoxide and hydrogen. This mixture of carbon monoxide and hydrogen is called water gas or synthesis gas. If air is passed over hot coke, nitrogen is produced along with carbon monoxide. The resulting mixture of carbon monoxide and nitrogen is called producer gas. Water gas and producer gas are important industrial fuels. The carbon monoxide in these mixtures can undergo further combustion. This produces carbon dioxide and liberates a great amount of heat. Carbon monoxide is a powerful reducing agent. When exposed to metal ores, it reduces most of them to the elemental form of the metal. Note that carbon monoxide cannot reduce the alkali and alkaline earth metal oxides, aluminium oxides, and the oxides of certain transition metals. Reactions with carbon monoxide are used to extract many metals from their ores. The reactions here show iron 3 oxide and zinc oxide producing iron and zinc. In the process, carbon monoxide is oxidized to form carbon dioxide. Since the carbon in CO has a lone pair, it can act as an electron pair donor. Therefore, carbon monoxide can react with certain metals when heated to form metal carbonyls. Several types of metal carbonyls are illustrated here. It binds to the Hem group of hemoglobin 300 times more strongly than oxygen. The hemoglobin molecule is, thus, prevented from transporting oxygen. This can ultimately lead to death if not treated promptly. Home carbon monoxide detectors are available and can be life-saving. Now let's turn our attention to carbon dioxide. Carbon dioxide is also a colorless, odorless gas, but it is non-poisonous. It has very low solubility in water. By volume, 0.03% of the Earth's atmosphere is carbon dioxide. Try to answer this problem on your own before proceeding. Consider the carbon dioxide molecule. What is the hybridization of the carbon? How many sigma and pi bonds are present in the molecule? The carbon in CO2 is sp hybridized. The molecule has a linear geometry. As shown in the illustration, the sp hybrid orbitals overlap to form a sigma bond with each oxygen atom. Each unhybridized p orbital on the carbon overlaps with an orbital on each oxygen to form a pi bond to each oxygen. Notice that the pi bonds are at an angle of 90 degrees to each other. The most important Lewis structure for carbon dioxide has both the oxygen atoms double bonded to the central carbon atom. The carbon-oxygen bonds are 115 picometers in length. The carbon dioxide molecule is non-polar. Although the carbon-oxygen bonds are polar, the bond dipoles cancel. Two other resonance structures shown here can also be drawn for carbon dioxide. There are several ways to prepare carbon dioxide. One way is by the combustion of either carbon or carbon-containing fuels such as methane in excess air. In the laboratory, carbon dioxide can be prepared by reacting dilute hydrochloric acid with solid calcium carbonate. On a commercial scale, carbon dioxide can be prepared by heating limestone, CaCO3, until it decomposes. In water, carbon dioxide reacts to form carbonic acid, H2CO3. Carbonic acid is a weak diprotic acid. It dissociates in two steps. First, carbonic acid loses one hydrogen ion to form a hydrogen carbonate ion. Then, the hydrogen carbonate ion loses its hydrogen ion, resulting in a carbonate ion. Both carbonic acid, a weak acid, and hydrogen carbonate, a weak base, are present in blood. Having a weak acid with its conjugate base forms a buffer system that maintains blood pH between 7.26 and 7.42. It is very dangerous for the blood pH to fall below the normal range. By using chlorophyll, plants make their own food through photosynthesis. This process removes carbon dioxide from the atmosphere. The ultimate product of photosynthesis is the glucose molecule C6H12O6. Heat from the sun warms the earth. Radiation is re-emitted and then reflected by the Earth's atmosphere. This is called the greenhouse effect. There are increased concerns that rising CO2 levels in the atmosphere may be contributing to global warming. Dry ice is the common term for solid carbon dioxide, which can be formed by allowing liquefied carbon dioxide to expand rapidly. It is used as a refrigerant for ice cream and frozen foods. Carbon dioxide has many uses. It is used to prepare carbonated beverages. Because it is heavy and does not support combustion, it is used in fire extinguishers. It is also used in the manufacture of urea, CN2H4O. Quartz has piezoelectric properties. This means that quartz can generate an electric field when mechanically stressed. This property of quartz is used to manufacture extremely accurate clocks. Quartz is used in modern radio and TV broadcasting as well as in mobile radio communication. Silica gel is used as a drying agent and as a support for catalysts and chromatography columns. Kieselguhr, a form of amorphous silicon, is used in filtration plants. Silicones are another important class of silicon compounds. These organosilicon polymers have a monomeric unit of R2SiO, where R is an alkyl group that repeats many times. Let's see how silicones are manufactured. First, methyl chloride, CH3Cl, is reacted with silicon in the presence of a copper catalyst to form methylated silicones. In addition to the dimethyl dichlorosilane shown here, trimethylchlorosilane and tetramethylsilanes may also be produced in small amounts. Next, the dimethyl dichlorosilane is hydrolyzed, as shown in the reaction. Finally, the straight-chain polymer is formed by condensation reactions. To control the length of the polymer, adding trimethylchlorosilane blocks ends the chains. Silicones are water-repelling in nature due to the repetition of non-polar alkyl groups along the chain. This makes them useful for waterproofing fabrics. Silicones generally have high thermal stabilities, meaning that they are stable in high temperatures. They have high dielectric strength, which means that they can withstand high electric fields without breaking down. They are essentially inert chemically. They are resistant to oxidation and to most chemicals. These properties of silicones make them very useful. Silicones are used as sealants, greases and electrical insulators, as well as for waterproofing fabrics. They are also used for surgical and cosmetic implants, as they are biocompatible. Silicates are another important class of silicon compounds. Many silicates are found in nature, including feldspar, zeolites, mica, and asbestos. The main structural unit of silicates is the ion, SiO4-4. This polyatomic ion has a tetrahedral geometry around the central silicon atom. The tetrahedral units of silicates may be joined together at the corners by sharing oxygen atoms. Silicates are thus able to form chains, rings, sheets, or three-dimensional networks, as illustrated here. Two important silicates are glass and cement. Aluminosilicates form when aluminium atoms replace a few silicon atoms in silicon dioxide. Since an Si atom with a +4 oxidation state is replaced with a +3 aluminium ion, cations such as sodium ion, potassium ion, or calcium ion are needed to balance the charge. Zeolites are hydrated aluminosilicates. They are microporous, with tiny cavities in their structures, as shown in the illustration. Zeolites have a variety of uses. They are used as catalysts in the petrochemical industry. For example, in the cracking of hydrocarbons. They are also used in isomerization reactions. For example, ZSM5, shown here, is used to convert alcohols directly into gasoline. Zeolites are also used as ion exchangers to soften hard water, that is, water with a high mineral content, especially calcium and magnesium ions.